Okay. Okay, it's a great pleasure to have Kasia Rejzner. I'm probably mispronouncing it, but
no, it's correct.
Visiting from York, and she's going to tell us about BV formalism from physics to mathematics and back. So please, Kasia, we will interrupt you as we go.
Yes, thank you so much. It's a great pleasure to speak here, at least virtually. And yes, I do encourage to interrupt me so that we can have a conversation about this. This says that this is time to start the talk. All right. This is going to be a very broad overview of what I'm doing. So first, I want to tell you something about perturbative AQFT framework. So this is the framework I'm working in to understand perturbative QFT. And in particular, I want to talk about the BV formalism, how it fits into it. So I start with the classical BV, and then I will tell you about the formation quantization thereof and how the quantum theory is built. So that's the plan. Okay, so let me start with algebraic quantum field theory. Some of you might know that already, but it's always worth recalling for those of you who might not be so familiar with it. So it's a framework for investigating conceptual problems in QFT. So it's related to the axiomatic QFT, and it was developed by Hagen Kassler, also Araki, in the 60s. And the idea was to study quantum field theory by specifying, the observables that can be measured, can be considered in bounded regions of spacetime. So it was all Minkowski spacetime back then. So one takes regions of Minkowski spacetime and assigns algebras of observables to these regions. And in a very sort of naive way, you want to, of course, if you go to a larger region, then you want to be able to measure more observables. So if there is an inclusion of region, what should follow is the inclusion of observable algebras. And this whole thing has a structure of a net. So what we do in AQFT, we look at nets of operator algebras. And there are some axioms that are required. And let me just mention two for the sake of this talk. This is going to be enough. So one is causality. So it has something to do with, nothing travels faster than light. So if we have two regions that are space-like separated, then in some sense, whatever happens in those regions should be independent. Hence, we want the corresponding operator algebras to commute. So here, the commutator is taken in terms of the larger region where both of these are contained. So that's causality. And another is time slice axiom. So it has something to do with the well-posedness of initial value problem. So if you have a Cauchy surface and take the neighborhood thereof, then you should be able to reconstruct the information about the full theory of, the full region whose Cauchy surface it is from the information in the time slice. So this is something like, quantum version of the initial value problem. And these two axioms are kind of easy to translate also to curved spacetime. And the next step of generalization is to move away from Minkowski and go to curved spacetime. And another step of generalization is to drop some of these requirements on the algebras themselves and allow for the use of perturbation theory. So this is the main topic of my research, the perturbative AQFT, which is, essentially takes some of the ideas of AQFT about, this net of algebras and some of the axioms that can be used there, but then we do away with some of the requirements on the structure of these algebras. So we don't require them to be Von-Neumann. We don't require them to be C-star. We do with general involutive general star algebras that can also be algebras of formal power series. So this is this assumption, and that allows us to build locally covariant QFT models. So this works on curved spacetime as well. So as I said, it combines the idea of locality, causality, and so on of AQFT with methods of perturbation theory. And let me mention some people here that contributed to this subject, that made the subject what it is right now. And well, the first step in the construction, which I'm going to talk about, uses deformation quantization of the free theory. And this is something which was developed by Deutsch, Hagen, and Brunetti in 2000, various combinations. And then the way we introduce interaction uses Epstein-Glaser renormalization. And this is much older. This dates back to the 70s. This is a causal approach to renormalization, which is mathematically rigorous, which doesn't really require us to subtract infinities from infinities. Might talk more about it later, but it's very well adapted to this idea of PAQFT. And finally, something which is relatively new, all things considered, is generalization to gauge theories using methods of homological algebra. So the first step towards it was done in 2007 by Stefan Hollands, who wrote this beautiful paper about quantizing Young-Mills. And then in 2011, with Klaus Rennhagen, we figured the general framework using this Batalin-Vilkovisky formalism, how to quantize any theory with local symmetries within that framework. And this is what I want to focus on today. So I want to say something about this BV framework and how this provides a sort of overarching approach, overarching idea, how to construct models in PAQFT. Okay, so that was sort of the outline. And now let me come to actual, meat of the talk. So this is how we do things. We start with the following input. So somebody gives us a globally hyperbolic spacetime. So globally hyperbolic means that it has a Cauchy surface. Cauchy surfaces are great. Another thing we need to know is what sort of fields, what sort of objects we want to describe. So this is described by the choice of configuration space. For now, I'm not talking about any dynamics. So configuration space means just the kind of thing you want to study. So scalars, vectors, tensors, whatever. And typically, this is just some space of smooth sections of a vector bundle over M. So somebody gives us that vector bundle, and then we know what fields we have in the theory. And here are the examples. So the free scalar field is just smooth functions. Young-Mills, this is a bit more complicated. Assuming trivial bundle, these are one forms with values in some Lie algebra. For effective quantum gravity, which is another thing I play with, these are just metric perturbations. So various kinds of configuration spaces. And you can, of course, build in your whole field multiplet into this story.
Can I ask a question?
Yes, of course.
Is there an assumption that there are no Cauchy horizons?
Yeah, so, right. So globally hyperbolic, it means that it is foliated in Cauchy surfaces.
Yes.
So
D-theta is globally hyperbolic, but there are horizons.
Yeah, right. So globally hyperbolic is enough.
Okay.
So there is no further assumptions, just globally hyperbolic. That's all we need.
Okay.
And yeah, well, hopefully it becomes clear later why this works. We sort of work locally, so that's part of it. Okay, so and then the dynamics, and here we have to use something covariant because we work on curved spacetimes. So we want, we do have foliation into Cauchy surfaces, but we don't want to use it explicitly. So Lagrangian framework is actually better than Hamiltonian in that regard, because we don't have to make explicit use of foliation into these time slices. So we are using a covariant version of the Lagrangian formalism. More about it in a minute. And now let me start with specifying what are my classical observables. So in the first approximation, okay, I want to take all smooth functionals on my configuration space. So classically, I assign a number to a configuration when I make a measurement. And for my mathematical convenience and comfort, I want these to be smooth because some of these structures I want to introduce require differentiation. So smooth is good. And everything is happening now on some fixed globally hyperbolic manifold. So I'm going to drop M from the notation going forward. And now here's an important notion. So I want to be able to localize things. So I want to be able to assign these observables to regions. So I need some sort of way of doing this. And this is where the support of a functional comes in. So I define a space-time support of a functional as follows. So this essentially contains all the points of space-time such that if I perturb a field around that point, so you see, I have a field phi and the perturbation psi that's supported somewhere in the neighborhood of that point, then the functional takes notice. So these are all the points where the functional f is sensitive to perturbations in the neighborhoods of these points. It is something like the distributional support of a distribution. So if f was a linear functional, then this is the same as the distributional support. So that is sort of motivation for that definition. And furthermore, we can now also ask for more properties of these functionals. So we can try to, have some notion of niceness. And one notion of niceness is being local. Local is great. Local, that means that it can be written as an integral of some smooth functions that depends on the finite jet of a given field at point X. I'm going to be super lazy, so fields are called phi. Doesn't matter what's the configuration space, I'm dropping all the indices that are there. So phi is a field, no matter how many components it has. So jk of x, jkx of phi is the jet of phi at point X. So local is what you expect. And then often I want to be able to take products and sums of local things. So multi-local is a sort of algebraic completion of local undertaking sums and products. But that's not always enough. So there is a stronger assumption of being regular. And this has something to do with functional derivatives. So a functional is regular if all its derivatives seen as distributions on appropriate powers of m are smooth. So if you want to get some sort of intuition, what things are regular? Well, example of regular things would be a linear smeared field, so something which is linear in phi, and all products thereof. So products of linear things, linear smeared fields are regular functionals. And this is a very strong assumption, but sometimes it's useful to consider that class of functionals. Okay, so these are just the whole menagerie of things I want to consider. And now finally, I get to introduce some dynamics. So this would be pretty boring without any dynamics. And here, I want to talk about Lagrangians, but there is a bit of a technicality related to the fact that my manifold happens to be non-compact. So globally hyperbolic cannot be compact, unfortunately. So the Lagrangian has to be understood as a map which takes in a cutoff. I need a cutoff to make the action functional well-defined to local functions.
Kasia,
Yes?
when you say compact, you mean that the four manifold is not compact?
Yeah, so the Cauchy
sections can be compact.
Yeah, the Cauchy surface can be compact, but then you have to cross it with R, right? So this is where the problem starts. And if you think that you can just compactify it on a circle, well, that doesn't quite work, right? Because closed time-like curves. So yeah, a globally hyperbolic is non-compact. And here's an example of a generalized Lagrangian. So I take this cutoff F, I multiply it with my honest to goodness Lagrangian density for the free scalar field. And this is how I get my generalized Lagrangian. So it's what you think it is, but with that cutoff F. And here are other examples. So I have the guy for Young-Mills theory. I have the one for the Einstein-Hilbert action. So all of these now have to be with a cutoff. And this would be, of course, pretty embarrassing if I couldn't get rid of that cutoff. You know, nothing should depend on that little technical assumption. Well, here is how you get rid of the cutoff in the definition of the dynamics. So I want to define the Euler-Lagrange derivative of S, which I denote by ds, in a way which is independent of the cutoff. So here's what I do. I choose a cutoff F, and then if I consider a perturbation psi, so I want to know how the form ds of phi evaluates on psi. If I consider a perturbation psi has to be compactly supported, I can always choose the cutoff F so that it's one around this support of psi. So this is the condition. And then I can do it for any perturbation psi. I can always choose large enough cutoff. And this definition gives me then a form ds, which is independent of any of these choices. So ds is now honest to goodness form on the configuration space. So that's why, I call it ds, because this is what it is. It's a one form, it's a differential of S, just taking into account this cutoff in the intermediate stage.
What is the volume form you're using? D mu
sorry?
G. What is that volume form d mu G?
That's, yeah, so this is the canonical invariant volume induced by the metric G. So, square root of minus the determinant times the usual stuff.
Okay.
So yeah, so that's what one usually takes. And here is the field equation then. So I have this one form, which is sort of Euler-Lagrange derivative of S in this generalized sense. And then the field equation is the condition that ds of phi is 0. So the solution space is a 0 locus of that form. So I can now forget about these Lagrangians S and just think about these one forms that give the dynamics. And this I shall do. So that was dynamics. Now I want to talk about symmetries, because my whole story is going to be about BV, so symmetries play an important role. And I want to understand symmetries in the first sort of like a general level as some vector fields in the configuration space. So this is a cartoon. This blob of blueness is the configuration space of this big infinite dimensional thing. And in this, you can see these arrows representing vector fields, so directions in E. And then, well, you have a point, and you have, so functionals are then maps to C. So functional maps phi to C, and then these vector fields give you a direction at each point in the tangent space. So it's like in usual manifolds, but you have to take care of some functional analysis as you go along. And now I want also to consider vector fields that are multi-local and compactly supported, as I did with functionals, because that works. And they act on functionals as derivations. So I'm using this partial x as a derivation induced by x. How do they act? Well, I take the derivative of f at a point and contract it with the value of the vector field at that point. And this contraction is, well, practically speaking, this is the integral over the whole manifold of the corresponding two functions. So one of them is always compactly supported. Okay, and now I can do the same with actual action. So I can take the one form I got from the action and I can contract it with my vector field. And this map now from vector fields to functions, I will denote by delta S. So the subscript S is just remembering that this comes from a given Lagrangian. And now I can say what's a symmetry. So a symmetry is a direction in the configuration space in which the action is constant. So this is again very much like you imagine this should work in classical mechanics, right? So a symmetry should be the direction of constant S. And in terms of this funny little notation, it means that delta S of X is identically 0. So then that makes X a symmetry. So this way I have a sort of, geometric notion of what symmetries are in my story. And now I want to put this together into what I announced at the beginning, so some sort of homological framework. So I have the space of solutions. I want to find some nice interpretation, some nice description for the space of solutions. So first of all, I consider things that, well, I'm not interested in. So there are functionals that vanish on the solution space. I denote those by F0. And these are kind of redundant information, something which is not affected by the physical space of solutions. So these are typically of the form delta S of X for some vector field. You can very easily see why it goes one way. So if we just go back one slide, this delta S of X is always something that vanishes on the solution space because ds vanishes on the solution space. So clearly everything which is of the form delta S of X vanishes on the solution space. Now, it's not automatic that this is all there is, but this can actually be proven. So in a large class of theories that includes everything I want to talk about today. So, Young-Mills, gravity, standard model in particular. So all honest, good physical theories have that property that all the functionals that vanish on shell can be obtained as delta S applied to some vector fields. And this is an old result. This has been proven by Mark Eno and collaborators a while ago in a different context, in a different sort of mathematical setting, but it's still true. So we can assume this thing safely. So with that, the space of on-shell functionals, what is it? Well, I quotient all the functionals modulo this redundancy, what I'm not interested in. So my space of solutions is F modulo F0. So if I want to do some homological algebra, let me start with an exact sequence. So I summarize all this information as follows. So I have delta S as a map from vector fields to functionals, and its kernel is made out of symmetries. So I put them here in the next slot. And this delta S, I can finally now drop some names. So this is called the Koszul differential. And I can build the Koszul complex by taking the external power, so taking the graded symmetric algebra of this last bit, so V delta S to F. This is called the Koszul complex. And well, if I assume that there are no non-trivial local symmetries, so this guy here doesn't have any non-trivial local symmetries. By non-trivial, I mean not vanishing on the solution space. Then, well, first of all, in 0 degree, we have that the zero homology is the space of solutions. Well, that's always the case. But if we don't have any non-trivial local symmetries, then all the higher homologies vanish. So that this causal complex becomes what's known as a resolution of the space of solutions. Okay. Are there any questions to this?
You did not give the boundary operator in the complex.
The boundary operator is delta S.
Delta S, okay.
Delta S, yeah. So in this complex, if I just take this straight causal complex, delta S is the boundary operator.
I'm wondering, are there any complications if I've got topological terms in the action, such as a theta term in Yang-Mills?
Yeah, so there are various complications. So first of all, right, so yeah, you might want to add more symmetries. So I'm going to talk about it in a minute. If you have topological terms, you might want to actually look at the version of the BV formalism with boundary. So this is kind of describing local symmetries. So things that, I mean, are sort of compactly supported, localized in the bulk. If you want to describe a topological theory, you might be better off with the BFV formalism, where you have differentials in the bulk, differentials on the boundary, differentials on the corner. I'm not going to talk about it today because this is a finite time, but I will discuss it briefly in the sort of outlook section. So this is a kind of ongoing thing at the moment.
Can I ask one more question?
Sure.
It looked to me, I mean, you multiply the Lagrangian density by a compactly supported function, small f.
Correct.
That looks like what Bogolubov does in his old work. Eh?
Yes.
But now, the question I'm asking is, are your equations of motion involving local data, or is it on the entire time slice?
So I'm working with actions that are local functionals.
Okay.
So the equation of motion is just, it's local, it's a differential operator.
But when you evolve it for
right.
finite time or finite time, in the global,
so if correct. So if I want to evolve it, then well, if I want to have time slice axiom, then essentially I need to make sure that the dynamics is given in terms of evolution of the Cauchy data.
Or the entire Cauchy data. Because I was again wondering about this existence of Cauchy horizons.
Yeah.
Will block you from evolving local data, which can.
Yeah, well, right. So let me just come to the sort of dynamics part, and then we can maybe discuss it when I have sort of particular setting. But yeah, let's come back to it because I think it's an important thing to discuss. Okay, but so on this level, this is very general. I'm not even talking about the time slice axiom yet. So this is just algebra on that level. So it doesn't really depend on the details of the structure of the space of solutions. Okay, so let me now make a short interlude just to fix the notation. So in this context, people talk about things called antifields and anti-brackets. So I want to make sure that we all understand this formalism. So here, well, we have vector fields, right? In the finite dimensional situation, you could write vector fields in terms of, the derivatives, partial derivatives. So if you kind of go and run with it, you can think of the infinite dimensional vector field as sort of having these components, x of x, and the basis for these infinite dimensional vector fields would be given in terms of derivatives. So this is slightly formal, but not that much actually. I mean, it's very close to being precise because the way that the vector field acts as a derivation on a functional is essentially by plugging f into this functional derivative. So this kind of gives sense to the notation. And therefore, you can think of these derivatives as generators of the space of vector fields. And in the literature, these are called antifields. And the notation is very often either dagger or double dagger. And they provide the grading for this Koszul complex. So the number of factors of these antifields gives you the antifield number. So this is a grading of the complex. And of course, geometrically, this is just the order of a multi-vector field, right? So but honest to goodness, vector fields are order 1. Then you have higher multi-vector fields if you take graded tensor products. And there is also a bracket. There is the Schouten bracket, which is the commutator of multi-vector fields. Sorry, that's my clock. Yeah, this in this context is called the ante-bracket. Ante-bracket is just the Schouten bracket of multi-vector fields. And here is a nice thing. So I can write this derivation delta S almost as an inner derivation with respect to that bracket. Only again, I have to play that game with choosing the cutoff in appropriate way, but modulo that, I can write for each given x, I can write delta S of x as a bracket with appropriate cutoff S of f. So this will become relevant later. And now let me come to symmetries. So the space of symmetries is by definition a Lie subalgebra of the space of all vector fields, but we want to give it some more structure. So I want this to be, in fact, a tensor product of some Lie algebra, which is a bit smaller and tensored with the space of all local functionals. And just to give you an idea what these things could be, so this Lie algebra for Young-Mills theories, these are smooth functions valued in some finite dimensional Lie algebra. And for gravity, this would be all vector fields on the manifold. So these are two examples to keep in mind. And you see that S itself, it's still finite dimensional, but not horribly so. There are various levels of being infinite dimensional in this story. At least it can be easily dealt with. And what are we interested in characterizing is on-shell functionals, so functionals on the solution space, invariant under these symmetries. So we already know what's Fs from my previous story, and now we want to look at the space of invariance within that. So gauge invariant on-shell functionals, this is what I'm going for. This is the observables in the classical theory. And well, there's another homological algebra gadget called Chevalier-Eilenberg complex, which nicely characterizes the space of invariance for a given Lie algebra action. And this is given here. So you take the dual of S, then exterior power of that tensored with the space of functionals. And the differential is gamma, that in degree 0, it gives you essentially the action of this Lie algebra on your space of functionals. So if you look here, so gamma of f, it should be now something in degree 1. So it should be one form on the Lie algebra. So it takes a Lie algebra element psi, and it spits out a functional, which is f acted upon by the derivation del psi. So this del psi is the action of your Lie algebra on the functionals. So this is the degree 0. And then in higher degrees, well, you have to take the commutator into account. And also there is a sort of graded Leibniz rule that you want to impose. So higher degrees can also be nicely fixed. But the important thing here I want to stress is that because of this particular action in degree 0, you know that if f is an invariant, then gamma of f is identically 0 because it vanishes for all size, all gauge parameters. So Now the cohomology is the kernel over image. So in this case, the kernel is all all gauge invariant functionals. The image is 0 because the thing starts at 0. So H0 of gamma characterizes the space of invariance. And this is exactly what we need from that structure.
Could I ask something?
Sure.
Since you're dealing with gauge variation of these functionals, have you got a possibility of discussing anomalies?
Oh, yes. Right. That's a very good question. So when I come to the full BV differential, then anomalies are in degree 1. They are in H1 of the full BV differential. That's correct.
Yeah, but I mean,
So,
even though, I mean, anomalies usually have some kind of topological existence, and even though you're using cohomological language, it's very algebraic what you're doing. I can't see any classical characteristic class theory or even anything.
well, so what you want to look at? Okay, so it depends what anomalies we're talking about, obviously. So here the anomalies come from essentially the cohomology of the Lie algebra action. So if you think about, let's say, Young-Mills theories, right? Then you have you look at the Lie algebra cohomology of your Lie algebra, which is then of course related to the Lie group. And then if you have something in H1, if you have something in degree 1 cohomology, then you expect that there might be anomalies. So this, for example, would register anomalies like the chiral anomaly in gauge theory.
But this is kind of formalism, because you've said you assume you have a hyperbolic manifold.
Yes.
Although the fact that the metric or the manifold is hyperbolic hasn't played an explicit role. It's just part of the assumptions.
Yes, and, not yet. I haven't finished.
And the lack of
yes.
the lack of compactness, and the anomalies will clash. I mean, if you really wanted to construct a kind of functional which was, say, trivial when there was no anomaly and non-trivial when anomaly was present, all these things would have to be present.
Yeah, it doesn't describe all the anomalies you're thinking about.
No, but even just one classical anomaly,
Yeah, it does describe one classical anomaly. So if you look at the work of Stefan Hollands from 2007, so he discusses that explicitly and shows that so he computes these cohomologies for that particular example and shows that the non-vanishing of H1 in this case leads to the breaking of certain word identities.
Mm-hmm.
So he does that calculation for Young-Mills. So yeah, and he uses also is very careful about these compact versus non-compact support.
Mm-hmm.
So I would kind of maybe kindly refer you to that work, and I'm going to talk a bit about it, but yeah, I think it's better to have a look at what Stefan did.
Okay.
Can I ask also this definition of gauge invariant on-shell functionals? There is all this work by Doppler, Hagen, Roberts. Okay, on algebraic.
Yes.
But they don't use Lagranges, but intrinsically define all these objects.
Yes.
And also Doppler and Roberts, I think, have a paper on localization of symmetries. Okay. How is this?
Yeah. So this is a bit of okay. So DHR is dealing with what I would call here global symmetries. So DHR is not really picking up local gauge symmetries. Why? Because DHR is looking at the algebras of observables. And so here, kind of the gauge symmetries are kind of redundancies of the description. So they wouldn't be picked up on the level of if I'm already working with invariants. So local gauge symmetries are not picked up by DHR. And as far as I know, there is no, general AQFT prescription. There is no version of DHR for local symmetries, for local gauge symmetries.
Yeah, they discuss global symmetries.
Yeah.
They have field algebras, which also encode.
Yeah, that's correct. But yeah, no, the thing is, right. So unfortunately, that analysis doesn't apply to gauge symmetries.
Okay.
But well, hopefully some sort of version of DHR could be could be formulated, but it's been a long-standing problem in the community, and we still don't quite know.
Also, may I ask, the local algebras of observables here are not factors, because
no, they are not even von Neumann algebras at this point. So they are not even Banach algebras. They are some topological, locally convex topological vector spaces. So
at some point one has to introduce a norm, no?
Sorry?
At some point one has to introduce a norm on the algebra.
Well, no, that's the question, right? Do you? So here I'm working perturbatively. So what I want to compute is kind of, well, maybe make sense of what people do with path integrals. So they're computing expectation values of green functions, right? That I can have states. Okay, I have this star algebra. I have states on this star algebra. I can compute expectation values of things, but I do not have a norm. A priori, you do not have a norm.
But the GNS construction will give them as operators.
Okay. So GNS construction also works for star algebras. So GNS construction would still work in that context, but would not give you bounded operators, would give you, in general, unbounded operators.
Yes, but that will define a norm on the operators. Okay, it can be unbounded, whatever. Okay.
Yeah.
Surely, if you have locally convex topological vector spaces, you must have norms there somewhere.
You can have semi-norms.
Well, that's very close. You can.
It is close, but it's not quite there, right?
Yeah.
I mean, it's yeah. If you have a Frechet space, then you're in a pretty good situation. But that's also not always the case. So for sure, you don't get von Neumann algebras out of it without any extra input. So does this answer the question? Sorry. I mean, we can, maybe after the talk, I can give you more details on the topology. I could, write this down explicitly, but it's not beautiful. So maybe let's postpone it to the later point.
Yeah, I think that's a good idea.
Okay. Okay, so let's see where we are. Okay, so let me just finish with this classical story with the BV complex. So this just combines these two aspects of on one hand symmetries, and on the other hand solutions. So gauge invariant functionals on the solution space, and this is a bit of graded geometry that some of you might appreciate, but if you don't know graded geometry, don't worry, it's not really relying on this. I just think it's a nice fact. So this Chevalier-Eilenberg algebra is really the space of functions on a graded manifold, where in degree 0 you have your original space of fields, and in degree 1 you have your gauge parameters. and these are kind of in physics called the ghosts. And this forms what I call extended configuration space. And now BV complex is the space of multi-vector fields on that. So again, if you want some greater geometry, this is functions on the shifted cotangent bundle of E. Sorry, this is a typo, this should be curly E. And it comes with two differentials. So in the first approximation, you can just take the sum of delta and gamma, so the Koszul and Chevalier-Eilenberg bits. And sometimes you need to add more if you have ghosts of ghosts, if you have symmetries between symmetries and so on. But
could
so
I
this,
ask, could you explain why it's shifted cotangent bundle? Because I know that Kevin Kostler has put forward work about this, but I've never seen a good explanation as to why it's shifted.
Oh, why it's shifted? Okay, so oh, that's simple. So if you, let's forget about the symmetries for the moment. If we have just the configuration space and the space of multi-vector fields, right? So the space of multi-vector fields is actually functions on the shifted cotangent bundle. And the shift is because you want your your vector fields to be to be odd, right? So multi-vector fields are anti-symmetric, on the fiber. So you want to flip the degree on the fiber. You want to have a degree shift.
Okay.
Right? It's because if you construct multi-vector fields, you take the exterior algebra. If you were not shifting, then you would take the symmetric algebra.
Ah, okay.
Right, and the commutator, and this is because the commutator is something anti-symmetrized, not symmetrized.
Okay, thank you.
And
can you give us a geometrical interpretation of ghosts? Are they dual to the Lie algebra elements? Or what?
Yes, correct. Yes. So if we go back here, you see that here I'm working on the dual. Okay. So ghosts are now elements of this S star. So they are functions on this graded manifold. They are functions on, of S which are graded.
And where do Gribov ambiguities come into this?
Oh, they don't. Sorry. So this is so this is a sort of local description, and it's a bit of local and derived description. So Gribov ambiguities would come up if I was doing if I was trying to globalize it, but I'm not. So this is like in the usual BRST. So
yes,
the usual BRST doesn't capture Gribov ambiguities. And this is just a way to package BRST into something larger, but it contains BRST inside.
But is this not a problem?
Why is it a problem? Why should it be a problem?
You are working locally on the bundle, presumably.
Yeah. So right. So my goal here is to construct local observables, right? So in that sense, I'm only working with local data, and also I'm constructing those local observables perturbatively. So as long as I still stay local and perturbative, I'm not bothered by the Gribov problem. If I want to do it non-perturbative, then obviously I would have to think about it a bit longer. But this goes beyond the scope of this, BV BRST formalism. Obviously, it's a good question, but the formalism does what it does and doesn't do what it doesn't. So no, it doesn't do Gribov.
You're not fixing gauge. You're not fixing the gauge.
That's a good question. So in this BV formalism, you can construct things where you fix gauge only. So I am fixing the gauge, but the way this is set up the whole structure is independent of the gauge fixing.
Now,
So
can you
this,
ask-
excuse me?
I just want to, in a causal complex, one takes quotients rather than fixing a section. Okay? And what I
Yes.
know is that there is a theorem due to Narasimhan and Ramadas. They are algebraic mathematicians who have proved that if you try to fix a gauge in Yang-Mills series, then there is no section, even locally there is no section, because the gauge orbit cuts the fiber infinitely.
Yeah. Okay,
over
then
of
I will
the
tell you
gauge.
how I fix the gauge later. I'm sure that theorem has assumptions, so there must be some assumptions that are not met here, because here you can fix the gauge.
Okay.
So I will tell you how I fix the gauge, and then you will tell me how it relates to that result. So yeah, so here is one fact. I haven't fixed the gauge yet. So here is one fact. So the general nonsense says that, well, because of the way we constructed things, the zero cohomology of S describes gauge invariant on-shell functionals. So this is fact number one. Now, let's see if I have, okay. I can talk more about gauge fixing. Yeah, maybe after this one. So sorry, I will come back to the gauge fixing. So yeah, so we have, again, this ante bracket, we have this Schouten bracket on the space of multi-vector fields. Again, we can describe this S as almost an inner derivation with respect to extended action. So we add extra terms to the action, which then correspond to also implementing the gamma differential. And then this action has to satisfy what's called classical master equation. So this corresponds to S being nilpotent. And well, obviously we are still working with this cutoff. So classical master equation is holds in the limit of constant F. Okay, so what are the ingredients I have here? So I have this graded algebra, BV, and I have the differential, which is actually described in terms of this extended action. So now gauge fixing. So what I can do, I can consider various equivalent descriptions in terms of quasi-isomorphic complexes. So I have the BV complex, and if I go to a quasi-isomorphic complex, then I don't change the cohomology, so I don't change the physical information. So gauge fixing is passing to a quasi-isomorphic complex where the extended action leads to globally hyperbolic equations in degree 0. So I'm transforming the whole complex such that the degree 0 is nice, that it gives rise to globally hyperbolic equations, but I'm not truncating anything. I'm just moving things around so that the degree 0 is nice. But in that sense, I'm not actually fixing the gauge. I'm just passing to a quasi-isomorphic complex. So does that address your question, Val?
Can you, what is quasi-isomorphic? Did you define?
Oh, it means, this just means that a complex with the same cohomology. A different complex with the same cohomology.
Well, I have to study your papers. Because
so there is a, like, at each level, there is a map between, there's a map on the chain level in each degree, and these maps are compatible with the boundary maps in each complex. So
what we know in the gauge context is if one passes to quotients.
Yeah, but I'm not passing to quotients. I want to make that clear. I'm not passing to quotients. I'm working on chain level the whole time. I'm not taking the quotient. I'm working on the co-chain level, so I'm working with the complexes without going to cohomology.
Okay.
I want to remain so because quantization is better that way.
You're saying you're not fixing the gauge, but the Faddeev-Popov procedure, which the BRST is a mathematical formalism of, does fix the gauge.
Well, no, no, because yeah, so yeah, it's so the BRST part is like only a part of my bicomplex. So you can think of it this way. So if I go back here, the full differential is a sum of delta and gamma. So gamma is the BRST part. So I'm not truncating anything in terms of delta. So delta is this sort of Koszul part. So I want to keep all the degrees. I want to keep all the antifields. Okay. So I can pass to the cohomology of the whole thing. I could pass to the cohomology of gamma. I could pass to the cohomology of delta. But for the sake of quantization, I want to keep all of it untruncated. I want to keep all the all the complex. But then on the level of calculating the expectation values, this is what Faddeev-Popov procedure does, right? I'm computing the path integral, so I compute the expectation value. Only on the level of computing expectation values, I actually take the cohomology, right? So I take degree 0 cohomology, which then picks up what this Faddeev-Popov procedure would compute. But this is kind of, I want to quantize the complex and then extract physical information out of it at the end, after it's quantized. Does it make sense?
Yeah, I think so, thanks.
Cool. Okay.
Is there any general reason why quasi-isomorphism holds in this situation? You said you can construct maps, but kind of
so the thing, the sort of basic package, so constructing this, this BV algebra with the extended action, this works for any theory that you have, equations of motion and symmetries. Now, the question whether you can find a quasi-isomorphic complex that has sort of nice behavior in degree 0, yeah, that's hard to decide on the general level. It's easy to decide in examples. When you do it, it's done. So essentially, right, you in the examples we know that it's done. But it's a great question. I wish I knew. It would be nice to have some sort of general way of saying, right, we can always pass to an appropriate quasi-isomorphic complex, but no, unfortunately it doesn't. It doesn't exist yet. Okay, so I have somewhat limited time, but I understand that I can just carry on. Am I right in that assumption?
Yes, you can continue, yeah.
Okay, great. So I came to the green function, so I can address one of Bal's questions soon. So this is now finally a bit more of quantization coming through. So let's start with putting some algebraic structures on this. So I have my differential operator for the three equations of motion. So in the scalar field case, which I want to consider first, my equations of motion for the free theory are just the Klein-Gordon operator applied to the field. And I know that for globally hyperbolic spacetimes, P admits retarded and advanced green functions. So these are the guys that propagate my Cauchy data. And these are the guys I need for my algebraic construction. So first algebraic structure I need is the commutator function, which is the difference between retarded and advanced green functions. So all I need for my theory to make sense is the global existence of these retarded and advanced green functions. So that's a sort of, any theory that has that is good to go. I'm not sure, Val, does it answer your questions with?
Yes, yes, I want to ask a question. What are the technical assumptions on delta R and delta for the existence of retarded and advanced green functions?
Yeah, they are green functions, right? So they are inverses of P when restricted to compactly supported configurations.
Yeah.
And they retarded propagates the support to the future, and advanced propagates the support to the past.
Sure. Do they always exist?
Yeah. So they exist if you have. Sorry, that's my clock again. If you have normally hyperbolic equations, they always exist. So there is this big book of Berginot and Pfeffler on wave equations on Lorentzian manifolds, where they construct these things for normally hyperbolic operators. And there are also papers of Christian Beer following that, where these notions are generalized.
Okay.
So that's the reference, but we tend to say that we want to work with operators that are green hyperbolic. This is the notion that Christian introduced. Green hyperbolic means it has retarded and advanced green functions as seen. So and then there is a discussion by Christian about in which situations you get those green hyperbolic operators.
Okay.
So this is kind of surprisingly powerful toolbox. Okay, so why do I need those? I take the difference and I get something which is called Pauli-Jordan function. And this allows me to construct first the Poisson structure, known as the Piles bracket, due to Piles, and then to deform it to a star product. So I do the deformation quantization. And here for the star product, I need some choice of a Hadamard state, 2-point function of a Hadamard state, if you're more physicsy minded, but sort of more mathematically, I need to choose a bidistribution, which has, I have delta as its odd part, as its anti-symmetric part, and H is a symmetric part, which is also assumed to be a solution to the equations of motion. So the whole thing also has to satisfy some wavefront set conditions for these things to be well defined for local F and G. This is again part of the standard lore in algebraic QFT on curved spacetime. So you need to be able to construct such objects, such Ws. And this is known for many examples. Yes.
So how much freedom do you have in choosing H? I mean, you don't have freedom in Minkowski space. So
you have lots because you can add any sort of symmetric. You can add any symmetric and smooth solution. So there is a lot of freedom. So what you construct is a whole family of equivalent star products. So this freedom is then.
Sorry, this is the freedom in the star product. This is the standard freedom of the symmetric part of the star product.
Yes, correct.
But if you want to choose W to be a Hadamard, it should come from a 2-point function on a Hadamard state, such as the Weitman function.
Yeah, for example.
How much freedom do you have there?
Oh yeah, as I said, so you can add anything. So first of all, you want this whole thing to satisfy the wavefront set condition, which essentially says that the singularity structure is that of a Whiteman 2-point function on Minkowski. And within that restriction, with that wavefront set condition, there is still very large freedom in choosing H. So the restrictions are positivity. The whole thing has to be positive definite. The whole thing has to satisfy the wavefront set condition and be a solution. And still there is a lot of freedom.
Okay, very good. Yeah, thank you.
So so that's it. And well, all these choices are actually lead to isomorphic algebra. So just pick one, and then you can construct your star algebra for the free theory, which is good. We have that done. And now let me come to introducing the interaction, which is maybe slightly more interesting part of the construction. And here I need to, just for the sake of this talk, not forever, for the sake of this talk, I want to restrict to regular functionals, so things with smooth derivatives. And now let me make some connection to path integral story. So first of all, I introduce something called time ordering operator. It's very similar to, it's an exponential formula, right? You exponentiate by differential operator, which means taking the second derivative and then contracting it with the Feynman propagator. So here is finally the Feynman propagator. It's a kind of generalized Feynman propagator because you are working on a curved spacetime. So you choose your W. So you choose your symmetric path, and then the Feynman propagator is the sum of retarded plus advanced green function plus that symmetric path you chose in the construction of W. Okay, and what is it? So formally, when you're on Minkowski, this, abandoning rigor for a second, this is the same as taking the convolution with the oscillating Gaussian measure with covariance given by the Feynman propagator. So think of this T operator as a sort of rigorous way of making sense of that path integral on the right-hand side, which has its own issues in Lorentzian setting. And this is how the translation now goes. So we use those to construct time-ordered products. Everything, works with formal power series at the moment. So we have to take that into account. And maybe I should explain the time-ordered. So it's called time-ordered because of these properties of retarded and advanced green functions. This time-ordered product of f and g is in fact the same as the star product of f and g if the supports are time-ordered. And if I flip the order of supports, then the order of f and g on the right-hand side also changes. I pick an interaction. So for the time being, it's a regular one. And now I can construct what's called a formal S matrix, which is a time-ordered exponential of that interaction. And I can construct interacting fields using the famous Bogoliubov formula. So I perturb the S matrix slightly by that chosen observable. Then I act with the inverse of the original S matrix and take the linear part of it. So this thing R lambda V is also known as the Müller operator of the theory. Okay, and I can also define the interacting star product. So I deform the free star product using this Müller map, which kind of intertwines between free and the interacting theory. And algebraically speaking, this is all there is to be done, because then I can pick a state on this star algebra where everything is happening, and then compute expectation values, compute these various correlation functions in a given state for the interacting fields. So that's the idea. And of course, I'm now not talking about the most important thing here, which is the renormalization problem. So why doesn't it all work as such simple algebraic prescription? Well, the point is that regular interactions, if they are non-linear, they are also not local. So there is a tension between things being local and things being regular. So your honest to goodness phi to the fourth term is not a regular interaction. It's very non-regular because derivatives contain the delta function, the delta distribution. So there are potential singularities in all these time-ordered products that have to be dealt with. So, okay, if I look back at this formula, I started with telling you that the time ordering operator is given as this exponential formula. But if I want to be really honest about things, I should instead use Epstein-Glaser renormalization to construct renormalized time-ordered products. So these time-ordered products would have to be constructed in a slightly different way if I want to deal with local interactions. Okay. So, but let us put that off for further discussion later. So that's the renormalization problem, generalizing this from regular to local. But now I want to say something about gauge theories because I don't want to go too much over time. And I think, well, it's important to mention that. So first of all, okay, we start with this extended action. We assume that we can set things up so that the extended action is nice. Yes?
Hello?
Hello? Hello?
I think it's just extraneous noise, sorry.
Oh, okay, okay, yeah, no, I thought there was a question. All right, so we assume that we can arrange things in such a way that the sort of quadratic term, the S0, has some nice behavior. And what is the nice behavior? So S0 is quadratic, so it can be quadratic in fields or linear in fields and linear in antifields. So I split it into these two pieces. So one is quadratic in fields, the other is linear in fields. And then the second derivative of this first guy, I denote by P. And the second derivative of the second guy, I denote by K. So the key assumption here, which is a make or break of the whole formalism, is that P has to be a normally hyperbolic operator. So green functions exist, okay? So one has to put some work into arranging things in such a way, finding this quasi-isomorphism so that the S00 of the extended action actually gives you normally hyperbolic operator. But that's all I need. I don't need to fix the gauge. I don't need to go to the level of cohomology. I just need this to be arranged in such a way that the order 0 has nice behavior. And the other condition which I also need is that K, this linear part, also has to have some compatibility with respect to W, with respect to my 2-point function. It has to be invariant under that K. And a kind of physical intuition behind it is that W, the 2-point function, has to be invariant under the linearized BRST operator. That's kind of the physics behind it. And again, this is nicely discussed in the paper of Stefan Hollands on Young Mills. So he discusses the construction of appropriate W so that this gauge invariance under linearized BST operator is fulfilled. Okay. Right. So this is a sort of, outline. It's very, it's a bit condensed. Let me just tell you a few words about what comes next for the BV operator. So the linearized classical BV operator is now the bracket with this as 0 with the quadratic part, and the quantum master equation So this is the first sort of non-trivial condition on quantization that comes from having this gauge symmetry possibly, or this BV extension of the story. So this is the compatibility between BV structures and this time-ordered product story. So the time-ordered exponential of the interaction, the S matrix, has to be invariant under a 0, and this leads, if you expand things appropriately, this leads to an algebraic condition known in the literature as the quantum master equation. So the function S0 plus V functional fulfills quantum master equation if this expression in the bracket vanishes. And here we have a new feature. We have the BV Laplacian. So in that formula, the first bit looks like the classical master equation. So this is sort of classical, and we have a quantum correction, which involves a graded Laplacian, which is now purely quantum effect. So that's the first thing. So quantum master equation has to be fulfilled for your interaction, and this is where anomalies could happen. So if you happen to pick an interaction which doesn't fulfill this quantum master equation, you cannot arrange the renormalization freedom to make this work. Then you failed, you have anomalies, you cannot quantize this theory. Okay, and let me just tell you what's the quantum BV operator before I finish. So the quantum BV operator, the free quantum BV operator, is the twist of the classical BV operator by the time ordering map. So again, there is this classical part which we expect, and there's the quantum correction involving the BV Laplacian, and the interacting quantum BV operator is the twist of S0 by the Müller map, which could end up being non-local, but fortunately it doesn't. Sorry, so let me just skip to the result. So assuming that the quantum master equation holds, then this quantum BV operator again has this classical bit, which is the classical BV operator, and the and the correction coming from the BV Laplacian. Okay, and this is the guy you want. So this quantum BV operator, now its cohomology tells us what are quantum gauge invariant on-shell observables in the theory. Okay, so let me just maybe emphasize one important point here. My idea here is to sort of quantize theory by deforming that whole complex. So I'm deforming the products. I use that deformation to also deform the differentials, and then everything else comes out sort of automatically. So the important slide was here, that the quantum operator, quantum differentials come just by deformation of the classical differential by appropriate maps, which also deform the products. Okay, I think that's enough information for one day. Let me just briefly discuss some perspectives. So the ongoing work, first thing we want to, I want to understand how all of this can be generalized to non-perturbative setting. So some sort of like finite BV complex story. And my feeling is that it should be possible to connect this to the recent work of Buchholz and Fredenhagen on the sister algebraic approach to interacting quantum field theory, which was done for the scalar field, but being able to generalize it to gauge theories, I think, would also address this question of non-perturbative version of the BV complex and word identities. So that's one ongoing project, and part of it is a work in progress with Brunetti, Ditch, and Fredenhagen. We are trying to understand quantum Noether theorem in by kind of combining, these homological things with the ideas of Buchholz and Fredenhagen. And another ongoing thing has something to do with the boundary. So there is a version of BV called BV-BFV, which also takes into account the boundary. And this is a project with Michele Schiavina. So these are the open directions. And sorry for taking forever. Thank you very much for your attention. Thank you for the questions. And yeah, that's it.
Well, thank you very much, Kasia. And it's open. Just before I go on, what did that on your previous transparency or slide, what did MWI stand for?
Oh, that's master word identity.
Oh, okay, sorry.
Yeah,
okay.
yeah. So well, I didn't go into details on that because of time, but when you are renormalizing the theory, fulfilling the quantum master equation, let's see if I have that slide. Okay, here it is. So fulfilling the quantum master equation amounts to proving the anomalous master word identity. So here again, I'm referring to Stefan and to the paper of Brennecke and Dutch, and then showing that this anomaly term can be removed by appropriate renormalization freedom.
Okay, thank you very much. Let me leave the floor open to other people's questions. So the floor is open. Who has a question?
So can I ask?
Sasha. Yeah.
Hi.
Thanks for joining us.
It's very nice talk. Thank you very much. I mean, so my question is kind of naive about the star product. So it's kind of like functional Moyle, or in the case of non-trivial interaction, it will be functional Kontsevich product, right? I mean.
Yes.
So
well,
my question.
Yes, only exactly. That's exactly the same thing.
So the question is kind of naive. I mean, so could you ask the question? Could you do something what Cataneo-Felder did to look for something like non-perturbative formulation of that product? I mean, could you look for some infinite dimensional sigma model in such a way as to give non-perturbative formulation to that? And what would be the physical meaning if, let's assume that you found that sigma model.
Yeah.
So what would be relation to that sigma model to the actual original QFT which you try to quantize?
Okay, that's an awesome question. It's a question I'm trying to answer as well. So there are two parts to the answer. So first of all, this interacting star product as it stands here, there is a paper of Eli Hawkins and myself where we made non-perturbative sense of that for regular functionals. So there is a combinatorial formula which also involves some graphs that gives you non-perturbative expression. Well, okay, so maybe there is a caveat. So non-perturbative in the coupling constant, but still perturbative in H bar. So it's a formal deformation quantization, but non-perturbative in lambda, which is good. Now we have also compared that with what would naively come out from the Kontsevich prescription, and it turns out, not surprisingly, that it's not equivalent to Kontsevich prescription, because Kontsevich prescription wouldn't work in an infinite dimensional setting. That wouldn't be well defined. So yeah, so we have a non-perturbative formula, and I would really like to understand if it can be described by a Poisson sigma model. Indeed, I think that's a great question. I don't know, but I hope so. I hope that there is some sort of, Cataneo-Felder story behind it as well. That would be big progress.
Thanks. But I mean, like you don't have any intuition. What would be the? I mean, will that sigma model have some physical meaning, or it will be just some formal tool to generate the perturbation theory? Yeah.
So my feeling would be that it would be rather a formal tool than some physical meaning behind it. But who knows? Maybe. But my feeling at the moment is that that would be just a formal tool.
Okay. Thanks. Nice talk again. Thanks.
Thank you.
Other questions?
can I ask a question following up on Sasha? Oh, somebody else wants to talk.
Yeah.
Hold on. You want to ask a question?
No, that's okay. Does somebody else want to pop in? Just want to give
Shall I
other
ask
people a
them?
chance in case they're.
Okay. So I will ask the question. I am following up on Sasha. Suppose I take in the free, let us say without interaction, just the free case. Suppose I consider a Hermite state.
Yes.
In the fields, okay. Then I extend it as a quasi-free state on the entire algebra. Okay. Then I have a GNS construction. So that will give an algebra of these field operators by the GNS construction.
Correct.
Is that the same as the deformation answers of, I mean, how is it related to deformation condensation?
Okay, so you can take, right, so this is, actually it all happens in the free theory. So let me go back here. So you have this star product, right? You have the involution. So you get a star algebra here. You pick a state. So you can obviously pick the one you started with. So you take this Hadamard state. And for that, you can do this generalized GNS construction where you don't have a norm. So you just work on the star algebra and you get representation as unbounded operators densely defined on some Hilbert space. Okay, and then so then it's the usual thing. So the vacuum in that GNS representation would correspond to this Hadamard state you started with, and then vacuum expectation values are expectation values in that Hadamard state. So this all works like the usual story with the GNS.
Yes. How is it related to star product? So once I have the algebra extending the Hadamard state as a quasi-free state on the full algebra, I get algebraic. I mean, I get a algebra. It is on C, so I get a star algebra.
Yes.
How is that related to this star here? You're writing.
All right. So I mean, there are two stars, right? The product of my algebra is the star product, and this other star is the conjugation. Is just a complex conjugation.
Yes.
So the product of the deformation quantization generated product is the product of my star algebra.
Okay, great. That's what. Second question is, second question I have, when you say boundaries, are you talking about Scri plus and Scri minus as in Minkowski space, or something else?
That's a good question. I was thinking more about finite boundaries and situations where you have a finite boundary, but I have this paper with Michele Schiavina where we also look at asymptotic boundaries. So for Minkowski, yes, Scri plus and Scri minus. So there is this paper of Michele and myself where we look at QED and the free scalar field in that framework. So where the boundary is the boundary at Scri.
Okay, I have one more question. There has been some discussion going on about scattering theory. So if you have a global...
before we go to that, I think Bernard just wanted to get in for a second. Just maybe we can come back to it. I don't want to have it.
Come on. No, thanks.
Oh, sorry, you unmuted there for a second. Sorry, I thought you were.
No.
Okay. That's
so
okay.
shall I ask the question? Okay.
Come on.
If there is a globally hyperbolic space.
Yes.
The issue is, we have been having some discussion about the de Sitter case, okay? And the issue is, if there is it is globally hyperbolic, and the issue is there a scattering theory on globally hyperbolic spaces, in case, even if there are horizons, Cauchy horizons?
Oh, well, scattering theory, I would at least take asymptotically flat or something, right? I mean, scattering theory, I think it's developed much less than like the whole framework, because scattering theory, well, first of all, I would do it in asymptotically flat situations. And then, I don't think it's so well developed, I would say, going beyond Minkowski. It just in isolated cases. people have done something towards that. But
there is no formal obstruction. When one looks at it, I mean, scattering theory is using this. It is quite central to physics. I mean, most of the observations.
It is central to physics, but also, you know, local observables are central to physics. My claim here is that what this framework describes. Okay, so what I can describe is how to compute correlations of interacting fields, how to compute expectation values of interacting observables. So the framework computes correlations of local fields. That's what it does.
But you can,
yeah,
you can quasi-local fields. One can define quasi-local fields as in Agrawal theory. Can one has someone?
Yeah, but you know, you cannot do Agrawal like on the nose because you don't have, you know, enough sister and from Neumann algebras in the game. So sorry, that's my clock. So yeah, one would have to think of some generalization of Agrawal that applies here. It's a tricky problem. So I'm not trying to solve that problem. I leave it to other people who are great and who are thinking about it. I'm interested in local aspects of the theory, and I'm interested in computing things that can be actually extracted from these. And I think that, you know, computing correlation functions is already something that does relate to physics, is an interesting physical observable. But yeah.
These are closely related issues though. I mean, the freedom in your Hadamard state here, which gives you this this freedom in H, in the presence of Cauchy horizons, it looks like you can put structure beyond that Cauchy horizon.
Right. Yes.
Which will have a huge effect on H.
Right. But
we were discussing de Sitter in particular, where one might put some structure at the antipode, which would give a very different quantization.
Right, but I mean, from okay, so from the point of view of this analysis, right? So you know, mathematically, all these choices of H give you equivalent quantizations, and then physics tells you what state you want to look at, right? So kind of for me, the setting
it comes in. I mean, it's not so much in the star product. It's coming into your Feynman propagator the way you presented it.
Yes, correct.
And
but
now you have it quite different physics because of that.
Right. But this is more in the choice of a state, right? So you can correct for that choice of H by choosing a different state when you compute your expectation values. So when you compute your expectation values, you tell me what state you want to look at, and then I correct for the choice of H. So I can start with a different H, not the one you want to evaluate your correlations in.
That's again focusing on the structure of the star product. I mean, you have a huge freedom in the star product itself. I would think they're independent. You could have an H, I think it's the next transparency for our next slide.
Right. But these are so H. So the freedom in the propagator is fixed by the choice of the star product. So the Feynman propagator is fixed by the choice of W. So there's no extra freedom.
The Feynman propagator is, but the star product could have a different H in it than in the Feynman propagator.
Right.
They don't have to be the same.
No, they do have to be the same, I think.
Do they?
Because this is because I mean, if I want this to be really let's see, if I want this to be really the time ordered version of the star product, I want this to be true. I want the time ordered product to be the time ordering of my chosen star product. So that kind of ties the choice of Feynman propagator to the choice of the star product.
Okay.
Can I ask? It's a beautiful talk. I mean, I liked it. Impressive work. But I have one more question. I think maybe Denjo is talking about there is this Hormanda theorem on propagation of singularities.
There is that, yes.
It may be that if there are horizons, it will break, you cannot extend the singularity structure using that equation. I don't know, because it involves the light cones. That theorem involves the light cones. So
Yeah, well, as I said, for me, the important condition is the existence or non-existence of global green functions. If there is if I have the global retarded and advanced green functions, all these structures can be defined. So if that gets broken, then that's a different question. Then one has to think, how to patch various bits of your theory together. Then you have only local constructions and you have to patch them together.
Excellent. Yeah.
Which I think, people do interesting things. People also do things on non-globally hyperbolic spacetimes. So there are attempts of kind of trying to develop a similar framework for non-globally hyperbolic spacetimes.
How about ADS? ADS is not globally hyperbolic.
Yeah. For example, like that, right? So there are some generalizations, but yes, it's on case-to-case basis. It's not so well understood as globally hyperbolic part.
We were discussing de Sitter quantization in particular, which it seems that your structure sheds a lot of light on it.
Well,
I like it a lot.
I have to say, I'm not sure if I have done like anything really, new in terms of that. Like large parts of this sort of the quantization of the free theory, right? This has been done before me. So there are people in my community who have thought lots about de Sitter in particular. So there are works of Nicola Pinamonti and Thomas Hack on de Sitter specific, where they look at more particular aspects, related to cosmology.
I think there's an additional freedom which you have highlighted there, with your freedom to choose the Feynman-Green's function with some more generality, because it's not clear to me, at least, that the physics beyond the horizon should be treated in the standard way that is done in, for instance, Holland's.
Yeah, okay, that's a good question. Yeah, I'm not sure. Okay, so there are also sort of different viewpoints on how to construct the Feynman propagator, right? So here I say that what should fix the Feynman propagator is this property. So that's my sort of shtick. So Feynman propagator is fixed by this property.
But that, as you said, that just said that the two H's were the same in your Feynman propagator and your star product.
Yeah, right. But
that doesn't tie it down very strongly.
Sorry?
That doesn't tie it down very tightly.
Oh, but somewhat. so there are also like other approaches to constructing Feynman propagators that are more based on scattering theory. So for example, there are works of Rejzner and Simpson, where they construct Feynman propagators on asymptotically flat spacetimes coming from a different perspective. So they really want to think scattering theory. And this leads to different Feynman propagators than the ones you get by, fixing this.
Yes.
So yeah, whatever you need, right? So here, like for me, this compatibility between the Feynman propagator and the two-point function I use for my construction is really crucial. This is like sort of part of the algebraic structure. But yeah, I see the mathematical reason for doing it. I don't want to speculate on the physics of this. So I'm not sure. Yeah.
Okay. Any other question? Just
So can I, so just for myself to clarify, so I will keep on using the language of conservation. So symmetric part essentially is what was called like gauge symmetry of the star product. I mean.
Correct. Yes.
So
yes.
so in this approach, this gauge symmetry of star product is translated into the choice of the vacuum which you use to define the star, right? I mean.
Correct. Yes.
So it's more or less one-to-one correspondence to this. So because I mean vacuum is in some sense what will define your damar.
Yes, that's right. Yes.
Okay. So
yes,
so meaning that meaning that that's why it's kind of a gauge, because I mean you don't mess up with the algebra. The star product depends on two inputs, the algebra and the state on it. I mean, so the algebra of course is all the time the same, but I mean the choice of the state will define your damar.
Is it? Yeah. So that's absolutely right. So the choice of the state corresponds to the choice of a gauge, but I wasn't using the word gauge because it means
I understand.
something different for gauge theories. But yeah, that's exactly what it is.
Okay. Thanks.
Okay. Do we have maybe I will stop the recording at this point. We've a reasonably long recording, unless there are other questions you want recorded. Okay. Thank you very much for the talk, and I will stop.